motion.
Welcome back to Physics in Motion. I'm so glad you could join us as we take another deep dive into the world of physics.
We're here to break down those tricky concepts, make them a little easier to digest.
And hopefully have a bit of fun while we're at it. Today we're tackling a topic that might seem simple on the surface.
But trust us, there's more to it than meets the eye.
We're talking about acceleration. Now, you might be thinking,
Acceleration, that's just about things speeding up, right?
well, get ready to have your minds blown because there's a whole lot more to it.
It's not just about going fast, it's about how quickly your velocity changes.
Okay, I think we need to break that down a bit.
Absolutely.
We know many of you are in 10th grade, maybe starting to wrap your heads around physics and chemistry.
Let's make it relatable.
So picture this. You're at a drag race.
Two cars side by side.
Revving their engines, the anticipation is building,
One peels out, accelerating forward.
while the other blasts backward in reverse.
They're both accelerating, just in opposite directions.
So it's not just about speed, but direction too, right?
Exactly. Positive acceleration means you're speeding up in the direction you're already moving.
Like that car zooming forward.
Precisely. But the car going backwards.
It's accelerating too, just negatively.
Because it's changing its velocity over time in the opposite direction.
So negative acceleration isn't always about slowing down.
It's about the direction of that change in velocity.
So how do we even measure this change?
We use the units meters per second squared, or MSY.
Oh, Emeth-wise. I remember this tripped me up in school. What does it even mean to, square a second?
Think of it this way. If you're accelerating at 2 meters whirls, your speed increases by an extra 2 meters per second every second.
So it's like speed itself is gaining speed.
You got it.
Okay, so if I slam on the gas and go from 0 to 60 in 5 seconds, that's some serious acceleration.
You're experiencing a large change in velocity over a short period of time.
Now, get ready for this. Can something have no speed but still be accelerating?
Next.
I'm talking completely still yet accelerating. Seems impossible, right?
Not at all. Imagine tossing a ball straight up in the air.
Okay, I'm picturing it.
At the very top of its arc, for a split second, it hangs there.
Motionless. Before falling back down.
That moment, right at the peak, the ball has zero velocity. It's not moving up or down.
So it's just frozen.
Not quite. It's still accelerating because gravity is constantly working, pulling it back towards Earth.
So even when the ball is momentarily at rest.
Gravity's still acting on it, causing a change in velocity, which means acceleration.
Wow. That completely changes how I think about motion. There's always more to it than meets the eye. But why does that ball fall back down? What's the driving force behind that change in motion? And what about those mind-boggling speeds needed to, escape a planet's gravity? How does that even work?
Those are all great questions, and they lead us to even more fascinating aspects of acceleration. We'll explore the forces behind those changes in motion and even how acceleration can affect how much you weigh.
You're telling me acceleration can change how much I weigh? We'll have to dive into that more after the break. Stay tuned because this deep dive into acceleration is just getting started.
Welcome back to Physics in Motion. Before the break, we left you wondering about what makes things speed up, slow down, or change direction.
And we promised to talk about how acceleration can even affect how much you weigh.
Right, let's tackle that weight question. Imagine you're standing on a scale in an elevator.
Okay, I'm in the elevator, standing on the scale.
As the elevator starts moving upward, what do you think? Would you feel heavier, lighter, or stay the same?
I think I'd feel heavier. It's like when a plane takes off, you get pushed back in your seat.
You're exactly right, and it all comes down to forces and acceleration. When the elevator accelerates upward, it's exerting an additional force on you, pushing you upward.
So I'm pressing down on the scale with more force, making the reading go up.
Precisely, it's what we call apparent weight. You experience this all the time, even in a car.
Like when you slam on the brakes and you feel yourself jerk forward?
Exactly, that's inertia, your body's resistance to the change in motion, making you feel a force.
Okay, that makes sense. But we still haven't talked about those crazy speeds needed to, break free from a planet's gravity. Remember that space shuttle? It needed to hit 28,968 kilometers per hour to escape Earth.
Right, that's escape velocity, the speed an object needs to overcome gravitational pull. And it's not just a random number, it depends on the planet's mass and how strong its gravity is.
So a massive planet like Jupiter, with its super strong gravity, would have a way higher escape velocity than Earth.
Absolutely. Think about the Juno spacecraft orbiting Jupiter right now. It had to hit almost 217,000 kilometers per hour to get captured by Jupiter's gravity.
6 times faster than escaping Earth. That's mind-blowing. Speaking of mind-blowing, remember those velocity time graphs we mentioned earlier? You said we could actually see how acceleration changes by looking at them.
Exactly. If the line on the graph is straight, that means acceleration is constant. Think cruise control on a highway.
Steady speed, smooth ride.
But if the line is curved, that means the acceleration itself is changing.
So we can tell if acceleration is increasing, decreasing, or like doing something totally wild just by looking at the shape of the line.
You got it.
That's so cool. It's like a secret code to understanding motion. Now, we keep talking about changes in motion, but what actually causes acceleration? Like, what's the driving force behind it?
That's where forces come into play. Forces are what cause changes in motion, and therefore acceleration is all connected. In fact, Newton's second law of motion states that acceleration is directly proportional to the net force acting on an object.
Hold on, net force. What's that?
It's not just about how much force is applied, but the direction too. Imagine you're pushing a heavy box across the floor. You're putting in effort, you're applying force.
But there's also friction working against me.
Exactly. The net force is the combination of all those forces, considering both their strength and direction.
So it's like a tug of war between my push and the friction.
Exactly. If your push is stronger than the friction, the box accelerates forward. If friction wins, it might not move at all.
So to really understand acceleration, we have to understand forces too. It's like a whole chain reaction.
You got it. And speaking of chain reactions, let's shift gears to something equally fascinating, where objects move at a constant speed but are still accelerating. Circular motion.
Wait, constant speed and acceleration, how's that even possible? I thought those were opposites. Wait, constant speed and acceleration, how is that even possible? I thought those were opposites.
It's one of the most counterintuitive parts of physics, but think about it this way. Acceleration is about the change in velocity, and velocity includes both speed and direction.
So even if something is moving at the same speed, if its direction is changing, it's still accelerating.
Exactly, and that's where circular motion comes in. Imagine a car going around a roundabout.
Okay, I'm picturing it,
Its speed might stay the same, but it's constantly changing direction.
which means it's constantly accelerating.
You got it. And that acceleration always points towards the center of the circle. We call it centripetal acceleration.
Centripetal acceleration. Sounds intimidating.
Well, like any other acceleration, centripetal acceleration is caused by a force.
Okay, so what causes it in this case?
In the case of that car on the roundabout, it's the friction between the tires and the road that provides the centripetal force. It's pulling the car inward, keeping it from veering off in a straight line.
That makes sense. So if the road was super slippery and there wasn't enough friction, the car would just skid off in a straight line.
Exactly. You know, sometimes when you spin something and it flies off, the path it takes is along a straight line called a tangent.
Right?
That's what would happen without enough centripetal force to keep it moving in a circle. That's why it's so important to slow down when you're driving around a bend, especially if it's raining or icy.
You need enough friction to provide that centripetal acceleration. So centripetal force is basically what keeps things from flying off into space when they're moving in a circle.
That's a great way to think about it, and this applies to everything from merry-go-rounds to planets orbiting the sun.
Wow. It's incredible to think that this one concept, acceleration, governs so many different phenomena, from a car braking to a rocket launching into space to planets moving in their orbits.
And remember how we talked about that split second when a ball tossed in the air reaches its highest point? Even though it's momentarily at rest, it's still accelerating downwards because of gravity.
Right.
That's just another example of acceleration at play.
It's amazing how something that seems so simple at first glance turns out to be so complex and fascinating.
Right, and we've only scratched the surface. There's so much more to explore when it comes to acceleration and how it shapes our understanding of the universe.
Well, this has been an incredible deep dive into the world of acceleration. We've learned that it's not just about speeding up, it's about any change in velocity, which includes both speed and direction.
We've covered everything from positive and negative acceleration to those mind-boggling escape velocities.
And even how acceleration can affect how much we weigh.
We explored how forces cause acceleration and how centripetal acceleration keeps objects moving in a circle.
We couldn't have done this without the brilliant geeky gamer science teacher who created this amazing Physics in Motion series. A huge thank you for making physics fun and accessible for everyone.
Absolutely.
Until next time, keep those brains buzzing, and remember, everything around you, from the smallest atom to the largest galaxy, is in motion, all thanks to acceleration.
The journey has begun. Velocity and vectors, second to none. From rest to speed, force and acceleration, physics in motion. Physics in motion.